on.
Hi, welcome to our YouTube channel. In this video, we are going to talk about some basic concepts of a computer about the CPU. Our discussion is going to be based on the instruction cycle, also known as the fetch, decode, execution cycle, the instruction format, and then interrupt. I'll be talking about the instruction cycle or the fetch, decode, execution cycle. Now let's look at the instruction cycle. So for a single instruction to be executed by the CPU, it must go through a certain process, and this process is known as a fetch decode execution cycle or the instruction cycle. The instruction cycle refers to the basic process the CPU follows from boot up until the computer is turned off. So this talks about when we turn on our computer and tells our computer to do something or click on the computer. We have instructed the computer to do something. Then the CPU or the instruction goes through a certain process before it is executed. And this process is the instruction cycle. Now let's go deeper into the instruction cycle. The central processing unit executes instructions sequentially, meaning each instruction being executed. So all this point is talking about is that more likely it involves only one core, meaning it has to execute instruction one after the other. So like we can see from this point, sorry. So like we can see from this point, the core 1, which task 11 is executed before task 22 and 23, then in that order. So meaning it executes task 11 first, then goes to task 22, task 23, then in that order before the instructions are executed. But in most modern computers, the CPU executes instructions concurrently using the techniques of pipelining and parallel processing, which involves multi-cores and processors. So as we can see from here, you have 1, 2, 3, 4, 5, 6 cores being arranged on the same CPU board. So like you can see from the concurrent processing, we have task 2, task 11 and task 21 being executed at the same time, task 22, 23 being executed at the same time. So like you can see, in those days, the time used to execute an instruction was long, or it takes long to execute instruction in those computers. But in these modern computers, the time used to execute instruction is very small compared to those days because of the parallel processing and pipelining. Now let's move on. The instruction cycle comprises of three main stages, namely you have the fetch stage, the decode stage, and then the execution stage. Now let's go deeper into each stage. This is the fetch stage. From the moment we turn on our computer, the CPU is ready to process instructions. As instructions comes in, a special register in the CPU referred to as the program counter is responsible for holding the address of the next instruction to be executed. So as you can see from this diagram, the program counter here is responsible for holding the next instruction to be executed. The address stored in the program counter is copied into the memory address register. So as you can see from this diagram, the program counter, which is responsible for holding the address of the next instruction to be executed, is copied into the memory address register and then incremented for it to point to the next instruction to be executed. So from here we can see that from the program count after the instructions in the program counter is copied into the memory address register, the program counter is incremented to point to the address of the next instruction to be executed. So after the address of the next instruction to be executed in the program counter is copied into the memory address. The memory address register then copies it into the RAM, which stores it. After that, the CPU then copies the address described by the memory address register in the RAM, copies it into the memory data register. The memory data register also acts as a two-way register that holds data fetched from memory or data waiting to be stored in memory. So, like I said, memory data register acts as a two-way register. That's one is it holds data that has just fetched from memory, and the other one too is it stores data that is waiting to be stored in memory. So, like you can see from this arrow, it points to the memory, the RAM, and then it points back to the memory data register. Eventually, the instructions in the memory data register is copied into the current instruction register, which acts as a temporal holding grounds for the instruction that was just fetched from memory. So, as the instruction is fetched from the RAM into the memory data register, it then copies it into the instruction register, which acts as a temporal holding grounds. So at this point, the instruction is getting to the decode stage. Thank you.
Okay. What's up, everybody? My name is Samuel, and I'm into computer architecture. I'm here to talk about the decode and execute cycle. Okay, so the decode stage allows the CPU to determine what instruction is to be performed, so that the CPU can tell how many operands it needs to fetch in order to perform the instruction. The operation code fetched from the memory is decoded for the next steps and moved to the appropriate registers. Decoding is typically performed by binary decoders in the CPU's control unit. Reading the effective address steps can be embedded into the decode stage as it involves evaluating which type of operation is to be performed. If the operation is a memory operation, the computer checks whether it's a direct or indirect memory operation. With direct memory operation, nothing is done. However, if it turns out to be an indirect memory operation, then the effective address is an input or output register instruction. The computer checks its time and executes the instructions. Okay, so what this is talking about is, you see, as a normal individual, if let's say you go out to order some food or something from a restaurant, before the chef begins making what you are asking for, they have to first know what you want them to do. You get it, so that you can do it and present it to you. Yeah, so that's what I was talking about here. That's for the decode stage. Now, I'd like to talk about the execute stage. The CPU sends the decoded instructions as a set of control signals to the corresponding computer component. If the instruction involves arithmetic or logic units, the arrow is utilized. The execution cycle consists of memory read, memory write, input output read, input output write. This is the only stage of the instruction cycle that is useful from the perspective of the end user. Everything else is overhead required to make the execute step happen. The execute cycle is such that for n different opcodes, there are n sequence of micro operations that can occur. But this is a hypothetical example of this can be seen in the diagram above. From the diagram, the instruction adds the content of the location X to register R. To begin with its micro operation, we first address the instruction register containing the add instruction. The address portion of the instruction register is loaded into memory address register. The address field of the instruction register is updated from the memory buffer register, so the reference memory location is loaded. Content of R and memory buffer register are added by the arithmetic logic unit. A more complex example can be seen here in the diagram. Here the content of the location X is incremented by 1. If the result is 0, the next instruction will be skipped. If the result is 0, the program counter is incremented by 1. So what the executor tells us about is how the computer system goes about executing commands. So that's all for today. My name is Samuel. Thank you once more.
Hello guys, computer or any electronic device operates when there is an instructions given. I'm Joel Budalo and I'm here to describe instruction format. Instruction format is defined as a standard machine format that can be directly decoded and executed by the central processing unit. In other words, instruction format is simply a sequence of bits, which is zeros and ones, contained in a machine instruction that defines the layout of the instruction. We have types of instruction format, and namely, first is zero address instruction format, one address instruction format, two address instruction format, and the three address instruction format. In the zero address instruction format, it refers to the interface or devices that require little or no explicit detailed instruction for users to operate them, and it requires no field address. The goal of zero instruction format is to make the user experience as seamless as possible. Example of the zero address instruction format can be found in the modern technologies like Siri in the iOS devices, where one has to speak and automatically signals are sent. The CPU will execute it and the result will be given out. The second type of instruction format is the one address instruction format. And in this type of instruction format, the user only it has one field address, and it refers to providing instruction that are understandable and straightforward, requiring only a single step or action to be taken. The third type of instruction format is the two address instruction format, and it involves two different action or steps. This instruction requires the user to operate and to do two separate actions to complete a task. Example is when you want to on your laptop, you only have to press the power cord and press the power button, and the device will turn on. The last part of the instruction format is the three address instruction format. And in this type of instruction format, it refers to a single opcode with three fields of address. It has one address field which is used for destination, and two sources. And a typical example here And an example is the picture here. Thank you guys.
Hi class, my name is Jonathan Sakiti and I'm continuing from where my colleague ended about the instruction format. So the CPU, I'm here to talk about CPU organization and instruction format and how CPU decodes instruction format. A control unit processor, also known as a central processing unit, is a brain of a computer system. Each role involves executing instructions, performing calculations, and managing data within a computer. So the CPU organization, the CPU comprises the control unit which manages instructions execution, the and the arithmetic logic unit responsible for performing arithmetic and logic operations. The control unit directs the flow of data and instructions by fetching them from memory, decoding and instructions to determine their actions, and then executing those actions. Other components such as registers, buses, and caches contribute the CPU's functionalities and providing faster to data and instructions. This is the this is the CPU I was talking about. This is the arithmetic logic unit, the control unit, and the memory, the control bus, and data bus. This is the arithmetic unit, the control unit, and the register and the memory, which I was talking about in the last part of the slides. When you talk about the instruction format, the instruction format defines how machine code instructions are structured. Components of an instruction format typically include the opcode, which is also known as the operation code, the operands and addressing mode, which shows how operands are accessed. Examples of instruction format varies based on instruction types. Arithmetic might involve an opcode and two operands addresses, while branching could include a conditional statement and a target address. So here is the example of the machine instruction format. This is the addressing mode and the opcode, and here is the operand. And we also have the importance of efficient decoding. Efficient instruction decoding enhances overall processor performance by reducing delays in instruction execution. To optimize decoding reduces execution time and energy consumption by streamlining the process from fetch to execute. 3. Techniques like overlapping stages and instruction processing and microcode optimization, which tune the control signals, enhance decoding efficiency.
Hello guys, my name is Solomon Amateyama and I'm here to present a work on addressing mode, opcode and operands. Well, let's get started. So now we'll start with the addressing mode. So now when you say the addressing mode, what comes to mind? Well, the addressing mode or the term addressing mode refers to the way in which the operand of an instruction is specified. The addressing mode specifies a rule of interpreting or modifying the address field of the instructions before the operand is actually executed. Well, it is also referred to as the technique or rules used by processors to calculate the effective memory address or operand locations for data operations. It plays a crucial role in determining the efficiency and flexibility of memory access and operand manipulation. So now let's talk about the types. We have different types of addressing modes. We have the immediate, direct, the indirect, the register indirect, displacement, then stacks, etc. So now let's talk about the purpose of addressing mode. Now the purpose of addressing mode is that it serves to decrease the number of bits contained in an instructions address field, and it also provides user with programmable skills by providing facilities such as counters, pointers, and program relocations, etc. So now I'm done with the addressing mode, and I hope you understand. Let's go to opcodes. Now, opcode. When we say opcode, we have different names used for opcodes. We have the operation code, instruction code, etc. So now let's talk about the opcode itself. It is the portion of machine language instruction that specifies the operation to be performed. It is used when writing machine codes and tells the computer what to do. Each machine language, each machine language's instructions typically has both opcodes and operands. It is executed by the CPU. Besides the opcodes itself, most instructions is specified or specifies the data they will process in the form of operands. The computer system has an opcode for each and every functions given to it. Examples of opcodes are the add, subtract, out. Yes, so these are some of the examples of the opcodes. These are some of the opcodes. So it can be found in bytecodes. It can be found in bytecodes and other form intended for a software interpreter rather than a hardware device. So I hope you also understand the opcodes. Now let's move to the operands. So now the operands. When we say operands, what are operands? Operands are any object capable of being manipulated. It is commonly expressed in computer programming as constants or variables. An operand is it's a quantity on which arithmetic operations is to be performed. It is also called data. So now let's talk about the types of operands. The operands, we have the numeric operands, arithmetic operands, logical operands, relational operands, pointer operands, and many more. So these are some of the types of operands, and I hope you understand everything I've said here. Thank you guys for viewing, and see you later.
Hello and welcome. My name is Lawrence and I will be taking you through Interact. Interact is an English word which means stopping the continuous progress of an activity. And an interact is a signal from a device attached to a computer that requires the operating system to stop and figure out what to do next. And interrupts are signals generated by an external device to request the microprocessor to perform a task. Example is pressing a key on the keyboard or moving the mouse. So when you are using a computer, you are running a current program and you need to stop and figure out or run another program, an interrupt occurs there. And this interrupt needs to be serviced before you could continue with your current program. And when interrupt occurs, there are two, or there's an interrupt handler that handles all the processes. So when an interrupt is generated, the interrupt handler then comes to play. What is an interrupt handler? It is a process that runs when an interrupt is generated by hardware or software. So this is also known as the interrupt service routine or ISR. So the ISR handles the request and sends it back to the CPU. So here is a little chart of explaining further the interrupt handler. So current task, then the interrupt signal, then stop task, status of current task is saved, services the interrupt, and then goes back to the current program. When types of interrupts, there are two types of interrupts. These are hardware interrupts and then software interrupts. Okay, so we'll be looking at hardware interrupts first. Hardware interrupt occurs by the interrupt request signal from peripheral circuit. It is also an electronic signal from an external hardware device that indicates it needs attention from the operating system. Uh, this could be a keyboard, a mouse, a joystick, or any other peripheral device attached to the computer which will cause an interrupt. And then there are two types of hardware interrupts. These are maskable and non-maskable interrupts. And with a maskable interrupt, this is a hardware interrupt that can be disabled or ignored by the instructions of the CPU. So, meaning when we say it can be disabled or ignored, meaning the current task which is at hand could go to an end before the interrupt is serviced. So maybe you're on a game, you have a call, or there is an interrupt which needs to be serviced because it is maskable, you can let go of it and then finish a current program and then go back and service the interrupt. And non-maskable interrupt, this is a hardware interrupt that cannot be disabled or ignored by the instruction of the CPU. Meaning, with the non-maskable, when an interrupt needs to be serviced, whatever current program or current task you are doing is placed aside, the interrupt is serviced, and then it comes back to your current program. But we now move down to software interrupt. And a software interrupt is a type of interrupt that is caused either by a special instruction in the instruction set or by an exceptional condition. Okay, so there are 256 different types of interrupts. And some of these examples are hybrid, doorbell, level triggered interrupt, and edge triggered interrupt. And so explain the software interrupt further. This is an interrupt where maybe a program built into the computer already needs to be serviced. So with this, it's not from maybe a peripheral device that is attached to the computer. So and then we move on to advantages and disadvantages of interrupt. Let's start with advantages first. And it is fast and effective. It decreases the waiting time of the CPU. It enables multitasking by allowing the CPU to switch quickly between different processes. With one, it is fast and effective. Interrupt makes work easy. You can do this and do this very quick. It decreases the waiting time of the CPU. So maybe you waiting for this program to run fully before you can access another program, it's time wasting. But because of interrupts, you can stop this and then service this and come back. So it decreases the waiting time of the CPU. And three, it enables multitasking by allowing the CPU to switch quickly between different processes. Okay, so multitasking, you are on paint, you are playing music, you are doing this, and then another interrupt comes in. So it's quick and fast. So disadvantages. There is more load on the CPU. It reduces the efficiency of the system. Uh, okay, and causes and then sources of interrupt. Um, causes problem errors. The program performing an invalid operation. So maybe there's an operation that is not valid to the system. When performing that, it causes interrupts. And then page faults. The program referencing a page not in central storage. So needing something that you need for your current program, maybe you try accessing a page, but you don't have it in your system, so it will cause an interrupt, and then request to monitor an event. And then we move on to sources of interrupt. There are two sources of interrupt, which are internal and then external interrupt. Internal, internal interrupt. These are caused by some exceptional conditions caused by the program itself rather than an external event. They are generated by an on-chip peripheral, serial and parallel ports. Okay, so internal interrupt. This occurs when there are other devices connected to the computer, and then it works together to create that interrupt. And then there are external interrupts. They provide a means for your machine to respond to various signals operating from either inside or outside its configuration. They occur from connecting external peripherals to the processors. So connecting external peripherals to the processors, and this causes interrupts, which are external interrupts. Okay, so this is the end of interrupts. Thank you.